The next type of molecule that we are going to focus on in this diagram is this one, hold on, right here. All right, so I circled one there, I circled another one there. So you can see here that there is a a bunch of green hexagons all attached together, and then the whole thing is attached to a purple blob that's embedded in the membrane. Same thing over here. Look, here's my chains of green hexagons, and it's attached to this purple thing that's coming down into here. All right, so there's several examples of these in this diagram. There's one more back here. These are called glycoproteins. Glycoproteins. So as you break this word down, glyco has to do with sugar, and protein has to do with protein. So this molecule is a sugar protein. So there's no such thing as a sugar protein, really. I mean, proteins are one kind of molecule and sugars are another kind of molecule. But what we're saying here is that this molecule is a hybrid of the two kinds of molecules glued together. So the sugar part here is the green hexagons. And once again, you should recognize green hexagons as the monosaccharides that we talked about in Unit 1. So we have a bunch of monosaccharides chained together to make a short chain. This is a small polymer, like we saw before, and then that's then glued or attached by a molecular bond, like a covalent bond, to this purple structure, which is the protein. So it's a protein and a carb kind of hybridized together, stuck together to make this overall molecule. This is a chain of monosaccharides. So we've already seen the term monosaccharide, which was one of them on its own, a disaccharide, which was two of them stuck together. And we've also heard the word poly, like a polysaccharide, from many of them, like starch, was many of them all hooked together. This is somewhere in between. It's not many, but it's not just two. So a word for a few is oligo. So this is a word that we use a lot in science, and it means a few. It means not as many as poly, but more than one or two. So this part is an oligosaccharide, a short chain, more than a mono or a di, but not exactly a poly. So we have an oligosaccharide attached to a protein. The protein allows this whole molecule to get kind of embedded in the phospholipid bilayer, and then the oligosaccharide part is protruding out into the outside part of the environment. So this is the outside of the cell, and this is inside the cell down here. Now these molecules, these glycoprotein molecules, their function, well, their form, their shape is very descriptive of their function. These things function like antenna. So they should look a little bit like antenna, like maybe the old days and radio and TV antenna on your roof, or like an antenna from a bug, that's sticking out of its head. And the role of an antenna is to receive or pick up signals, right? So that's exactly what these glycoproteins' jobs are. They are basically receptors. So their job is to be a receptor, which basically means they pick up signals floating around your body. Now, what do I mean by a signal? Well, if I want to tell you something as a human being, I can communicate to you by sound. I mean, I could communicate by sign language if I knew how to do that, but we rely on sound, like I'm sending sound to you right now. That's how we communicate and pass information from me to you. But inside your body, you can't do that. Let's say your brain wants to communicate something to your pancreas or your liver. Your brain does not have a mouth, and your pancreas or your liver don't have ears, and your brain can't say, hey, liver, do this, or hey, pancreas, do that. That's not how they communicate. Instead, all the communication inside your body is mediated by molecules, little messengers, like sending the mail to somebody. So your brain will create a chemical or a certain molecule and squirt it out. The brain cells will squirt it out into the bloodstream. The bloodstream will transport this molecule, this special message, to the liver or wherever it's supposed to go. It goes right around the bloodstream. And so your liver cells are hanging out with these receptors looking for whatever might be flowing by. And they are constantly looking for messages coming from the brain, and the messages from the brain come in the form of these molecules. And so the liver has to be able to know when that molecule is present, when it's washing by, when the brain's trying to talk to it. And that's what these receptor, these little kind of things do. They look for molecules. So let me give you an example. If you're driving down the freeway, on the I-10, right, and you're driving along at 60 miles an hour, and then there's a semi in front of you, and the semi has a tire that blows out in front of you, and there's rubber flying everywhere, and you escape within inches of a fiery wreck on the I-10. All right. Now, you didn't die, nothing happened to you, but your brain, your eyeballs saw this thing happen in front of you, and your brain interpreted it as, oh my gosh, this is dangerous, something's going to happen, right? Now, although nothing happened to you physically, you're still sitting in your car and you're just like you were before, what is your body doing after you see that thing happen in front of you? And you probably like get really shaken up. You feel like your palms get sweaty, your heart starts beating faster, your breath changes, right? All those things are changing inside of your body. Your heart is suddenly beating faster. Now, did your heart see the wreck or see the flaming tire or anything? No, your heart hasn't got eyeballs. Your heart couldn't see that. So how, and the brain can't shout to the heart, beat faster. So how does, and you're not in any danger anymore. I mean, nothing happened to you, yet your body reacted. How did that happen? So the brain, the eyeballs see the potential hazard. The brain interprets it as danger, as imminent. The brain sends a quick signal electrically to the adrenal gland on the top, which sits on the top of your kidneys, and the adrenal gland squirts out adrenaline into your blood supply. And that happens really quickly. So all of a sudden there is now adrenaline molecules in your bloodstream. Now your heart is just hanging out in your chest, beating away as normal, but your heart muscle cells have all these receptors on them poking to the outside of themselves. So let's say this is a receptor for adrenaline. Most of the time, this little antenna is just floating around going, da da da, nothing to see here, no big deal, everything's boring, right? So it's ready, but it's not really detecting the signal. Well, as soon as those adrenaline molecules get squirted into your bloodstream by the adrenal gland, those adrenaline molecules suddenly start flowing by and they stick onto the receptor. So here comes an adrenaline molecule. And when it comes here, it sticks. This receptor can attach to it. And as soon as it attaches, this protein can detect that. And it can tell, oh my gosh, I just detected the signal. And it can tell the inside of the cell to go and do something. And in this case, it's going to tell the cell, you need to start contracting faster. I've picked up adrenaline in the environment. That means something's going down. You need to beat faster to be prepared to deal with a dangerous situation. That's the way that your body communicates over long distances by sending these chemical molecule messengers, and then you need these receptors to be able to pick them up. If you were missing this receptor, so for example, if you didn't have this receptor for whatever reason, it's gone, the adrenaline would still be squirted out into your bloodstream, but it would just wash by your heart. Your heart wouldn't be able to pick it up, and so your heart wouldn't respond. Even though the adrenaline was there, your heart wouldn't know, and it wouldn't know to beat faster. So having these receptors or not controls a lot of how you react, how your body is able to react to certain conditions. And there are definitely some diseases and conditions where people don't make receptors for certain chemicals, and if the cells can't see the chemical, then they can't react, and sometimes that can cause issues with development and other things. So that is the structure and role of glycoproteins.